Hi everyone, this is Julie Martinez-Hayes. I'll be doing this very quick video on an intense chapter. We are covering, first of all, this is for the CTI-120 class, and we're in the security half of the book. And this will be security chapter 4. Usually I break this up a little bit. It can be material reminiscent of your networking half, and sometimes by this point in the semester people's brains are pretty fried, so I try to break this up into two pieces. The first part of this chapter is actually a refresher on the OSI layers. We'll be covering some firewall issues, how to use VLANs well, what tunneling actually is, also a whole lot of security issues, types of attacks, hacks, buffers, floods, all kinds of things. But let's get to some of this easy stuff, and then we'll take breaks. So I will have break slides mixed in, and just pause whenever you need to. I'll try to get the table of contents up, but Camtasia was not playing very well with YouTube, so that didn't get uploaded properly. I think it's a YouTube issue from what I can tell. Alright, first off, that OSI layer refresher. This will be on you to go refresh. Please do not throw sausage piece away. Is my favorite because it starts with the physical layer at the bottom. Then I will expect you to go review. This is a good 5 or 8 pages of this chapter, so take the time to review it, because the OSI layers and knowing what layer you're on, where is this device, that's essential. You'll need to know the layers. What we're going to do is move straight on to firewalls, so if you need to pause right here, reread those chapters of the book, go refresh yourself, please do. Pause here and know your OSI layers. For firewalls can be pretty interesting because they come in different forms, and there's a lot of different styles, architectural designs you can use. First of all, there's hardware versus software, and hardware firewalls, there's actually a physical device that goes in the rack, in the server rack. They'll have at least a couple of ports. They may have direct cabling and console cables or a place to plug in your laptop, but the idea is that you have an interface that goes towards the internet, interface being a port with a cable that goes towards your circuit, and you have an interface that goes towards the switch that would be in your DMZ. So you have a device that's separating your outside from the inside of your network. It's basically a revolving door that lets some people in and some people do not get in. Some people, it could be packets, it could be traffic, it could be based on IP. There's a couple of different types. But basically you're creating a pocket of safe space before anything gets to your true network on the inside. They are designed to deny all. Nobody can get in, and then you configure it to allow either a protocol or a source IP or something of that nature. It depends on what type of firewall. You can actually have firewalls on the inside of your network. For example, you could separate one campus from another. You could separate offices from student areas, and you can set up a set of rules to block one or block access to. In some cases, you would have it wide open, and that is called any. That's the technical term for having all ports have any port can get to any IP address can get to any other IP address. IP, port, or protocol can get through to the other side. Sometimes this is useful simply to watch what protocols are in use before locking them down. There are other ways to do it, but having a firewall on the inside lets you troubleshoot as well as limit. So once you're watching what software is doing, you can create special rules to allow traffic that's initiated from one side to another. The most intricate office organization I ever worked with was not the military, by the way. It was a for-profit school that had an 8-port firewall on the inside of the network. So it was blocking and monitoring and restricting traffic from all aspects and all portions of the campus to other portions of the campus. So it really had a very intricate set of rules set up so that students could not request data from servers that were on the office side. It's pretty cool, actually. Firewalls can look very boring and typical, almost like a very, very tiny switch, almost like a router. You'd have to know what the devices are and what the interfaces are, and also what product it is. So Sonic Wall in this particular slide is a well-known device. They can be fancy colored. They can look like something like this, where it's a firebox that's just bright red and it sticks out. Whatever you do with your network closet, be sure to label the firewall so folks know what that is. You could have other employees come in and have to do maintenance, and they need to know pretty clearly which device is which without looking too hard at it. One type of firewall is an early design. It's packet filtering, and it looks at every single incoming packet and compares it to rules, whether it's allowed or not, and whether it's allowed from a particular IP to the IP that the destination is. So it's comparing every single packet against the rules, and if it didn't fit the rules, it dumps it. It's slow. It has to go through a whole list of rules before it decides what to do. And frankly, one of the things you see when you're watching the traffic on this is you're watching traffic try to work its way through this list of rules. It'll change what port it is. It'll try a different IP address and see if it can get through. It's a little scary because the firewall is constantly working. It is never not working at filtering some kind of incoming traffic. So the amount of traffic hitting your firewall interface, if you have a public-facing website, you're going to have a firewall protecting it, and it's nonstop. A circuit level firewall is actually much more intricate. It's much more elegant. It's a newer technology, and it's using layers. It's using transport layers, and it's creating a set of rules so that where there's a traffic originates from a particular place, it can be allowed to continue or it could be blocked. So if, again, the example of if students are trying to hit a database server at a different campus, it could just look at the source area or source VLAN and not allow the response. But if you were to say a web request to a more public facing server, different server in a different VLAN, it could just be Blackboard. It could be our public website, just an internal version of it. It could be go.waketech.edu, an intranet, and it could say, well, this is from a student section, but it's going to an allowed server, so we're going to let the response get back to that student. So it's traffic looking at the origin, the destination, and allowing the reply. Application level is another more intricate design, but they're busy. They're very busy. It's looking at it's a deeper analysis, but it's also examining for spam. It's examining for reputation, whether that website that you're trying to get to is good or not, based on what other servers have, what other sources have, its reputation. So let's say there's a lot of spam on the ads, the banner ads that are in wral.com, then the reputation could get out that that is a bad website. So if it sees you trying to go to that website, it could actually block the traffic just based on reputation. So it also would look deeper into whether something has a virus inside it. This is a slow process, and it's scouring. This is scouring all this traffic coming in. So it's tedious and it slows things down. One thing that you're looking at continually is the state of something. Stateful versus stateless. And the stateless is the less sophisticated kind, so it's just looking at the filtering rule, nothing more intricate. Stateful looks at more layers. It's looking further down, and whether it's a reply or not. That's stateful. And the stateful is more elegant and more appropriate for a DMZ. VLANs are cool. VLANs are a very intricate way of creating formatting on your switch. This is a switch layer, so it's layer 2, and you format each individual port to be part of a VLAN. VLAN is a virtual LAN. This is used for isolation, and you can a port can be a member of multiple VLANs. So when you're in a VLAN, you are in a group. Your port is in a group with some other ports. So it could be that all the podiums are in a port grouped together in a VLAN, or all the users are in a VLAN. Maybe the IT staff has their own VLAN. One design is actually a smart way to use a VLAN, which is when you're putting a honeypot in. A honeypot is a lure. It's used as bait for people trying to break into your network. You put it in a separate VLAN so that if it does get snatched up, that the traffic is isolated and from your rest of your network, and therefore your network is safe. VLANs are, I'll give you an example of how I used VLANs. The IT staff had a VLAN so their ports could access some servers. So servers were in a separate VLAN, IT staff were in a VLAN, and then traffic from, let's say that if the IT staff were VLAN 20, VLAN 20 traffic was allowed to the VLANs with the servers. It was allowed through. If I needed to work in a different building and needed to access those servers, I had to pick a desk because it was port-based. That means the cable coming out of that port in the switch goes to a particular PC. So I'd pick a PC that was usually empty in a nice quiet area, and I'd put it in both VLANs, so it was a IT staff VLAN as well as whatever department it was in, and I'd be able to access my servers. So I could work, it was like a satellite office by putting that particular port in both VLANs. I created another office for myself, which was nice when it got too crazy around my desk. VLANs make things more efficient by limiting traffic. Broadcasts are really the big thing it does in terms of blocking. Broadcasts don't get beyond the VLANs. Not all the other VLANs see it. That's a good way to just limit the amount of crap going through a switch that every single port sees. It limits that. You don't have to route through it. The rules itself just allow access. It's more like, since it's layer 2, it's more like a traffic cop. But it is switch programming, so the person that creates the VLANs, first you have to design it, and then someone who has access to the switch would have to format and program this code into every single port on the switch of all switches. So it can be tedious to set up, but once you set it up, it's a good thing to have in your network. Saves you some headache. You can do VLAN membership by Mac, which is great for portable devices. If you have a tablet that moves around or a laptop that you carry around to different meetings, as soon as that laptop hits and gets an IP address from the access point, you want it to be in a particular VLAN. So it's a superb way to use your wireless addresses and just say, we can't do this by port because you guys are moving around too much. So we're going to do it by Mac. And VLANs can work by Mac. They are a lot more secure. You can limit who sees what. I have an example here of the IT remoting into servers. So if students try to remote into servers, it gets denied. Even if it is an IT person. Doesn't matter who's logged on to the machine if you're using the port programming version. So if I could be an IT person, but just sitting at some user's desk, and I can't get to my servers. All right, so that's how it ensures some safety there. In terms of exceptions, Mac is really your best way to format to configure your VLANs. If you've got mobile devices running around, an IT person might just say, you know, I'm going to carry my laptop with me for every single ticket because that way I know I can get into the servers, and that would solve the problem. Routing can be done by software or by hardware. So we're going to cover the software version first. You can do it through your operating system. You've actually already done a lab with some routing, but it's a very small scale. It's a PC at a time. It helps for apps. It can point certain traffic to a certain direction, but you know, as soon as that operating system has anything wrong with it, the routing will stop. Also, any new apps get upgrades, and then it won't work as well. The application-based routing really isn't the smartest way to go if you are an organization planning on growing. You'll need to have something hardware-based so that if you get beyond, 3 employees or just a group of 3 people, you've got some help. Now, there are a lot of different types of hardware routers, and some of them are very simple. You can have a small device that's just a couple of ports, and you put it in there, and you've got your router has interfaces. Routers aren't very big. They don't have to be very big, but they can be fast. They can have a couple of ports that are fiber optic. It's a fiber optic device in there that you just for ports that's removable. Hardware routers are faster. They're more reliable. They don't get viruses. They're more complicated to configure. They're easily scalable. They also have, instead of an operating system, they have firmware that does need upgrades. So you will need to patch it, which is a little bit more of a headache, but once you do it a couple of times, it's really not that bad. It just takes practice. Overall, though, these devices are expensive. So if you look up a Cisco router and look at some prices, they're painfully expensive. They're not the kind of devices you would have in your house, but you might have some hand-me-down versions that you bought used and have those tested. Govdeals.com is a source of used hardware that government organizations use to surplus. When we are surplusing old hardware, we use GovDeals to sell it, and that's a good source for things like routers. The other issue with routers is that it takes higher skills, and the classes that we use to cover them specifically are Net 126, 225, and 226. I did not include Net 125 because that switches. So you will have to get the higher level Net classes to learn routing. How routers work have a couple of different methods. Link state versus distance vector are the two big types, and this is how it chooses a path. So it has to figure out how to get to the next hop, and the distance vector versus link state are the two ways it calculates it. And the big difference between the two is how is information exchanged, where is it stored, how much does it save, and if one of these devices goes down, how does it figure it out, and how does it figure out the new route? So they all have pros and cons like anything, and I'll give you an example of each. Distance vector is RIP, and link state would be OSPF. And now if you open S was what? Okay, if those letters look somewhat familiar, but the acronym isn't jumping out at you, open shortest path first, then go back and review that part of routing in your other book, because we covered this already. Just to review distance vector, routers dump in the entire routing table to all its neighbors, which means that each neighbor then collects its entire routing table and dumps it onto the next one. I say dump, it's really just share, but holy cow, those things get big really fast. And you can get caught into loops if someone builds an algorithm and say, oh, we go to this one first, and a different router says, no, we go to this other one first. You can actually watch traffic go full circle around in circles without getting to its destination. So that's a little tricky. Because of that, when things go wrong, they're more of a pain to troubleshoot. They need more storage. They have to get cleaned out once in a while, and they're limited. So they are limited to 15 hops, which means automatically, if you're trying to get to a server in California, you don't want distance vector, because distance vector is say, I'm going to limit you to 15. I will figure out what those 15 are. 15 hops will be, and then I'll get you there the shortest distance. It's once it hits 16, it is considered and it's maximized. It's basically aged, and it automatically gets dropped. So after 15 hops, at each hop it's adding one, and so you get to the next hop and it says, oh, I see that you're 1 hop plus 2. It's going to keep adding that. Oh, now I'm hop 3, now I'm hop 4, and once it gets to 16, it's dropped. It just drops. So it's not good for external use, just inside your network. Like I mentioned earlier, there are loops. You can have multiple paths going the same place, and if it redirects you the wrong way, it'll actually redirect back towards you. Count to infinity loops result from an outage where the router suddenly doesn't know which way to go. It's lost its route, and what happens is the route is recreated in different directions. So routers will then forwarded this traffic on and add a hop count, but yet it's sent to another router as well, and the hop count is added there. Then none of these might be the correct route, so the traffic doesn't get to its intended destination. So basically, it's like lost traffic. So I'll send it everywhere, and after 15 hops, it hits the 16th and it gets dropped, which basically means there's a whole lot of traffic going out there, and the intended data doesn't get where it needed to be. The way to prevent this, since usually the broadcast traffic that gets lost ends up getting sent back to where it came from, is a split horizon, which a split horizon prevents U-turns, so prevents any data from coming back to where it was sent, even if there's an outage. It just says, no, keep going forward, go that way. So it's having a built-in little sign to point the traffic where it needed to be. For triggered updates, basically as soon as when there's a change, it allows the update to be sent right away. So triggered updates just means there's an update and I need you to get sent it and now. This is how these routing tables stay up to date. So if you say, hey, there's a new server, or hey, the server got taken offline, that's going to change the math for everybody's route from there on. So having that information out quickly is important. Poison reverse is also a way to keep traffic from going backwards. It's called split horizon with poison reverse. Split horizon is to prevent U-turns, but the split horizon with poison reverse is an added feature that says not only are you going backwards, but because you're going the wrong direction, we're going to set the hop count already to 16, so the traffic automatically gets stopped right there. It gets dumped. So that's how it's poisoned. It's basically saying, yeah, you can't go that way, and by the way, you're useless, you're maxed out, and it gets dropped. Link state is a much smarter design. It's a smarter technology, and it's the one you would use on the outside of your network. Link state figures out who is nearby by sending a hello packet, so it knows what routers are nearby, and it builds a structure. It builds a list. They call it a tree, which is a map of the nearby networks. It does not save the entire route table of all of its neighbors and its neighbors. So the routing tables are much smaller, and it's not limited, so it doesn't matter if it hits 15 or 16 or 37. It can keep going. It just keeps sending out all the traffic. The updates are set faster, and this means faster convergence, which is data, voice, telecom all using the same network. So when these things are going faster, the traffic gets through faster. And if you're having video chat, this is the kind of thing that this is smarter and faster, but it's more complicated. So this would take higher skill level to configure. So you're looking at those upper level networking classes to configure this. And what's the smartest way to configure it? We're going to take a break here. So there is lots more, but we're mostly done with the beginnings of, the touches of routing that this book covers in this chapter. And I need you to just pause and go get some water, and we'll be back. Hi, we're back. All right, the next up is intrusion detection. We're going to be looking at different types of ways to get into the network and how to prevent it, which is key. So intrusion detection is finding who's coming into your network. There are several ways to look at this, sniffing and watching your traffic go on, but it's really better off in terms of mitigation. You got that word earlier in this book, to prevent the access. You want to close ports, you want to limit applications, you want to put things in the DMZ and limit what traffic gets inside to your network. So most intrusion detection is going to be network-based through a device or a copied port. You're going to often have a firewall with a port duplicator, which is called a mirrored port or network tap. So a network tap, it's a duplicated port. It's basically saying everything in and out of this port gets copied over to this other port. So it's an exact mirror of all traffic in or out, and it can be examined there. It can be examined on a separate port, which does not limit the traffic or slow things down quite as much, but you're examining it. You're taking a look at what's going on. What I see often is that by doing it this way, the traffic's already happened. The traffic's in, the traffic's out. So this is, by the time you're examining it and get around to looking at the results or the reports from this, it might be already too late. So, but this would help look at what is going on in your network overall, or what happened yesterday. Was there an attempted hack yesterday? Where did it get to? And then you can go fix it. So just know that network duplicators, it's already in. The host base can do the same thing. It's just a software way of copying all the data, traffic in and out, and monitoring it. And it can be run on a server. So you can install a product on a server that looks at all traffic coming through and then can maybe block it. That would be a firewall. Okay. Tunneling helps cover your traffic by putting it inside a different protocol. So this is also what was used when your IPv4 device had to talk to an IPv6 device. You could make one look like the other. Teredo was a tunneling and encapsulation technology protocol. That's the word I'm looking for. Another tunneling protocol is just PPTP, which is point-to-point tunneling protocol. It allows telecom, which would be things like fax lines, go through an IP-based system. If you remember, if you ever heard an old modem, dial-up modem connect and make a screeching noise, that was actually a handshake, so they could figure out what baud rate to talk at. It's like figuring out the common language. That was point-to-point protocol. So these protocols have been around. It was just converted. It was converted to allow to go through an IP-based system, and the LTTP is layer 2 tunneling protocol. It's the Cisco version of getting layer 2 through the IP-based system. Tunneling is a much needed protocol system to allow traffic of different types to communicate. They're like adapters. DNSSEC is a huge issue. There is a lot of security. There's tunneling layer security. You've got security at every single one of the OSI layers, and DNSSEC is particular to the DNS tables and the whole system of having a name linked to an IP address. This is also in conjunction with the IP address to a MAC address, which is the next layer, right? So DNSSEC prevents any poisoning of the DNS tables that have the name to IP number. And what it's going to do is do reverse lookups to convert and look back to say, are you sure you are who you say you are, to prevent spoofing. There's also ARP spoofing, which is changing what MAC address is linked to an IP address. DNS spoofing, similar, you're just going to it would intercept data and it replies to a DNS request saying, oh, you're looking for the mail server? Mail server's over here, and it gives an IP address of something else. So this spoofing is basically answering a request with misinformation that then gets populated to a table. So if someone's making a DNS request, that answer is getting cached somewhere, right? You have DNS tables locally, you've got DNS tables in switches, they're all over. So by spoofing, you poison that table with misinformation that then may get spread on, which is why preventing spoofing is really important. Sniffing is a term that can be very useful. It's a useful tool. It's also very passive. So sniffing is just capturing data. It's just a term to look at data or capture the data. Sometimes it's just viewing, sometimes it's capturing and viewing later, and then you can filter it. You can analyze it, sort it, filter it by protocol. If you don't know what's going on with your network, it really helps to take a data capture, just that you can then sort and filter through and tear apart and try to figure out what's going on. Unfortunately, it's really the most useful if you already have a data capture when things were healthy. So remember to stop and say, hey, it's time to get a sniff of this healthy computer to see how it's working so that I can compare later. And Wireshark is the tool you would use to capture the data. Now this may not be very visible, but this is an example of Wireshark. Just grabbing some data. Actually, not a whole lot's going on in this particular snip. I had to, was just quickly grabbing data that day. But you can sort by IP address. You can sort by source IP. You can sort by protocol. You can query for names. Several ways to manipulate it and get down to the relevant data. All right, types of attacks. It has a long list of types of attacks. So we have a couple of slides of these. Take a break if you need to right now. All right, one common attack, simply IP spoofing, which is changing the IP address of a certain either name or of a device. You would say, I want to be file server 1 and I want to pretend to be a different IP address. So it's going to skip the DNS security, would skip that and just plant the wrong IP address, or you can route IP traffic to you. So you're going to get around and say you claim to be a certain IP address. So that's really what's going on, is you're saying, like, I'm going to try to pretend to be this other device and collect all its data, which is really useful if it's going to be a domain controller and you're getting account information and passwords. All right, man in the middle is it's intercepting. It's grabbing the request and replying. I mean, you manipulate that request and then you let it go. So you're letting it go through. You're not like stopping it and sending it back. You're getting the request, the data comes through, you mangle it, and then you let it go. So wireless is probably the biggest area of weakness here, and having HTTP without any extra security is your biggest source, biggest problem. Not having security on wireless is just the biggest problem overall. Backdoor is actually kind of sneaky, and it's tough to prevent if people aren't paying attention, if they're rushed. Backdoor means security NAP was open and not properly closed, which means the port is still open, the ports are listening, and it may even have bumped up admin level credentials going through. So if you locked your computer with the console open to Active Directory where you were creating users or resetting passwords, then all that is up and running. So it's open and ready for use, and if anyone interfered and got to this traffic, it could use your open credentials and use that service. Hi, we're on another slide of attacks, and we're going to look at the DNS poisoning. That word should be attacked. Attacked cached DNS info. So DNS poisoning is looking at an upper level DNS table. So it would be something that feeds some users. So it's an upper level server, and what they're trying to do is attack the table and get into it and put in incorrect information, so anyone making a request to say Wells Fargo would get redirected to a different server entirely that might look like Wells Fargo, and someone might put in their credentials. A replay attack is another weakness of wireless, that data is captured, it's intercepted, it is modified, and then it's allowed to go on. So replay is similar to man in the middle, but man in the middle is oftentimes just viewing it as it goes by. Replay is actually stopping it, intercepting it, stopping it, modifying it. Your example in the book gave an example, used the example of an online purchase where the sending address was changed, and then the traffic was allowed to continue, so whatever was being purchased was redirected. All right, that was an example. That would be pretty tricky. So the timing would be a little bit off because the data is modified. Man in the middle is actually, it says it can be modified, but it's going through. You're watching it go by. Weak encryption keys, that's any kind of web. Weak encryption keys is really what WEP should stand for. WEP is an older technology that is easier to crack, and the problem is that older technology can still be in someone's closet somewhere in their house and have their home wireless easily cracked. You want to make sure that the technology you buy gets replaced every so often as the technology changes. You won't need to replace it every single year, but if you've got something in there that's over 5 years old, it might be worth replacing. Buffer overflow is one way to cause a denial of service. And what's going on is you send, if it's poorly written code, it's really bad code. So if you have a field that says type in your name, and if the code doesn't limit the size of this field, then someone just can keep putting in extra characters, extra info, and the buffer can't hold it all. And a couple of things could happen. Once the buffer is reached, it's dumped and then resent. So it keeps trying again, and that ends up with being the denial of service. The other thing that can happen is it goes to another nearby overflow buffer. I'm blanking a little bit on exactly how it happens, so I apologize for not explaining it, but one of the consequences of a buffer overflow is that you end up with root access. So either way, buffer overflow is a consequence of poorly written code, and anyone writing a single line of code should double check that if it's asking for data, how is it going to check that it's the right size of data? Social engineering is one way that people can convince other folks to cough up information or provide access, provide a badge, give a password. It can usually be from something good, like, oh, you've won this award, or hey, I'm delivering flowers for someone, I need to get into their office, or it can be fear. Your boss has asked for me right away and you need to let me in the door, that kind of thing. So social engineering has a lot of different types, and you could write a textbook on it. I'm sure you could see lots of YouTube videos of social engineering examples. Other password crackers, It's just a attempt to find the password and get through. Dictionary attack is just that. It's usually several dictionaries that are loaded, and one of them would be common passwords. And the password is checked against all of those all of those possibilities. The brute force attack should not be a comma right in between there. The brute force attack is a password cracking style of attack where each character is compared against all the possible other characters. So each digit of your password is compared against all 96 possibilities for numbers, letters, uppercase, lowercase, special characters. And then we try to go through, which means the longer your password is, the longer it would take to crack. And the trick there then, of course, is that the time that your password is allowed to exist before expiring should be less than the time it takes to crack. So denial of service, I mentioned one way already. A couple of ways to do it. Three separate types are measured, which one is a bandwidth, so it's volume based, and another one's protocol based, and another one's application layer. So volume based is just you're killing the bandwidth. A lot of different ways to do it. This can happen on many different layers, by the way. And it's just request. Protocol is when you're overloading. The firewall, the load balancer is what switches between, say, two NICs or two different web servers providing the same information. And if you're using a particular protocol, and there's still an overload to this. Application layer is using the get and post floods. So a get request and post floods. So get requests are more and more, you keep going through the gets, requesting more of that server until it can't respond to them all. UDP is a little bit different. A UDP flood, if you remember from the previous book, UDP is the protocol that does not wait for an answer. It doesn't care if all of it got through. So it's going to just keep sending traffic and not confirming or not waiting for an acknowledgement that everything got through. So UDP just kind of throws traffic through there, and whatever gets through and sticks to the wall, great. What UDP flood is doing is sending UDP traffic on a port and then a different port, and it's randomly changing what port. Now once it's used up a port, that port's listening. It's waiting for more. It thinks, oh, you're going to hand me, I don't even know how many, pieces of data I have to pass through, so I'll just keep listening until you're ready for me to pass on the next one. And if you send this on multiple different ports, they're all listening, which means they're all in use. And you're hogging all the ports because they're all waiting for the next UDP traffic to come through. And that floods that server. A SYN flood, SYN is for synchronize. When a synchronized packet comes through, it's waiting for an acknowledgement. Hey, did you get this? Yeah, I got this. Are you ready for the next one? Yeah, I'm ready for the next one. That's SYN-ACK. And if you keep flooding it with SYNs, the server is so busy sending ACKs back to it that it never actually accomplishes anything. A couple more types of floods and bombs. HTTP flood, which is what kind? Application. So you get a get or post requests from a web server, and it can't handle them all. So that's going to be requesting and keeps trying to answer. An email bomb is with attachments, and you can get really large attachment sizes by loading a PowerPoint file with a complete video. So it's one thing to put graphics inside a PowerPoint. It's another thing completely to put an entire video inside it and overload it with attachments. Most often, email attachment bombs are going to be something graphic design nature, music, something that can't be compressed. The ping of death is a malformed ping. Ping has a lot of features to it, if you remember from your earlier lab, in terms of how many pings it sends out, what size it sends out, and you can how many fragments. You can there's a lot of ways to manipulate a simple ping to overload a server. 0 day is when an exploit is just out, it's just been learned about, and it's brand new, and you're hitting it up. Yeah, so someone's writing malware to deal with that. We have some more, but take a breather here. Wireless security is huge. We have an entire course for wireless security. It's an advanced networking class. It is mandatory if you're doing any kind of networking, you need to do wireless. We live on wireless, so we've got to configure it. And just from the get-go of getting a wireless router out of the box, start thinking about security. Start thinking about changing the defaults. How are you going to lock it down? And there are some simple things you can do just with the wireless router out of the box. First of all, when you make a SID, which is your ID, you connect your devices to it and then you turn it off. So all your devices in your house are already connected to it and nobody can see what your network name is. Another trick is simply to not name it anything that makes any sense, that your neighbors can read and figure out who it belongs to. And random characters really do help here. The other is that whatever IP range, if it's 192.168.1. Whatever, change that. Change all the defaults. And frankly, rather than an IP range to give out, I actually like to use MAC filters. So not only do I have reservations that a device is going to get a reserved MAC address, or sorry, reserved IP address, and it will always get that IP address, but even getting to the server to the DHCP server that's giving out the IP addresses is based on MAC. So it's basically saying, I look at your MAC address of your device. If you're not in my list, you're not in the club and you're not getting an IP address. So another basic one that I didn't put up here, but I know I've covered before, is to make sure there's a guest wireless. So your devices are on the wireless that might be invisible. Make a separate guest wireless, and frankly, you can make that invisible as well, and let folks with a separate WPA2 with EAP, with stronger encryption, and let your visiting friends and their phones use that, and it doesn't touch any of your devices. If you have any questions, please let me know. I know this was a rush job. There were whole sections that I really didn't cover fairly well, and I'm flipping back through the book and looking at this secure socket layer saying, oh my God, I didn't cover this. This is a very big chapter. I know some topics we covered earlier, OSI layers you've covered earlier, NATing, NAT, when a group of devices are all point to the same IP address to get out. We've covered this earlier, so hopefully there's not too much in this chapter that's brain spanking new, but please email me if you have any questions. Thanks.